Okay, so we ended the first day by talking about cardiovascular adaptations, and cardiovascular and the respiratory system go hand in hand, as I'd like to believe you guys have realized. So we're going to do the same thing, only we're going to do respiratory adaptations. This lecture is a lot shorter than the cardiovascular one. And the funny thing is, I guess not funny, but this one will be probably half as long, but same objectives. So what are the adaptations, and then why do we have these benefits? Okay, it's important to know the lungs don't really change. Okay, so unlike your muscle that gets bigger, stronger, your lungs don't change. You don't develop more alveoli. You don't really get bigger alveoli or anything like that. There's just no change. But what happens is your ventilation will decrease. And this isn't a bad thing. This sounds bad. Like, if I'm exercising, why do I want to breathe less? Well, really what's happening is you're increasing your tidal volume, which allows you to decrease your respiratory rate. And so what's the benefit? Or is that you're taking up more oxygen with every breath. You're becoming more efficient. Adaptations are all about increasing efficiency. This is a big benefit. Okay? So by having a lower respiratory rate, we can extract more oxygen per breath. Okay, that's great. Another benefit is that you could look at it as that we're essentially reducing or eliminating or holding off on respiratory steal, right? If my diaphragm doesn't have to work as hard, or the rest of my respiratory muscles, I don't need them to produce ATP, which means I don't need them to take as much oxygen, which means that can be used by like my skeletal muscle, okay, by my legs or whatever it is that I'm doing to exercise. All right. So just kind of restate, if I reduce the amount of oxygen needed by my lungs, by my diaphragm, by those respiratory muscles, that's oxygen I can send over to my skeletal muscle, or the working muscle. So when we're at max exercise, we increase our pulmonary ventilation, and we do this by increasing our respiratory rate and our tidal volume. Eventually there comes a point where we can't increase our tidal volume anymore, or that it becomes cost prohibitive. Okay, we've talked about this a few times in class. Now, take a big breath of air in. Fill your lungs all the way up. Now breathe all the way out. And then if you keep doing that where you're filling your lungs up, you feel that tightness in your chest, and that's because you're stretching out your lungs, and they don't like it, and there becomes a kind of a law of diminishing returns, where, yeah, I can fill my lungs up, but I really have to generate a lot of pressure to do so, and that's not really effective. Okay. Now we can also look at it in terms of diffusion. The problem is during rest or even submaximal exercise, we don't really change diffusion. We have plenty of diffusion time, but during max exercise, our diffusion capacity increases, and you already know how this happens. This happens through increasing capillary recruitment. We increase our ventilation, so we have that alveoli recruitment. And then you can also remember, and this ties into this pulmonary blood flow, basically we recruit and we distend. So we can recruit and distend the capillaries. We can also recruit a few more alveoli. Okay. We have talked a little bit about this with the zones of the lungs. Remember, the top of your lungs, those alveoli are almost always filled up, stretched out because of gravity. Okay. Your lung is pulled open by gravity. However, at the bottom of your lung, due to blood vessels and the weight of everything above it, the alveoli at the bottom are more compressed, and so we can actually get air into them. This leads us into the AVO2 difference. Okay, remember, this is the difference in oxygen between the arteries and the veins, or in other words, how much are we extracting? Now, before we train, we can pull out about 50 mils of oxygen per liter of blood. We can pull that much out. This is at rest. At max exercise, we can triple that. So we can pull out 150 mils. Okay, that doesn't sound terrible. But after training, doesn't have any effect on rest, which makes sense because if I'm resting, my metabolic requirement isn't any different. But now at maximum exercise, I can pull out 200 mils of oxygen. Now, what this means is, it doesn't mean that if I run a 7-minute mile, that's maximum aerobic capacity or whatever, that I'm pulling out at 150 mils. And then after training, I run a 7-minute mile, that's still my max intensity, and I'm now pulling out 200 mils. What it means is I'm now going to a greater intensity that requires me to pull out 200 mils of oxygen per liter of blood. Okay, so doesn't have any effect on rest or submax, but it allows us to take up more oxygen at maximal exercise, which means we're going to have train at a greater or experience a greater intensity. All right. And so because of this, we say increased capillarity, or just think greater number of capillaries. We're going to be able to get more oxygen into our muscle. And this also is helped by the fact that we are doing a better job of redistributing blood flow. And those are the respiratory adaptations.